This is Lori Wall-Jesper and welcome to Numbering Systems. In this video you will learn that you already know all about decimal or base 10 and how you can use that knowledge to convert to any other base. We're going to demonstrate base 2, which is binary, and base 16, which is hexadecimal, because those are used in subnetting and in a lot of the computer area. You'll also learn how to convert between those. You already know decimals. You do this so automatically that you don't even think about what it is. But I'm going to break that down for you, and then once I do, you'll go, well, yeah, I know that. But then I'm going to take you into the different numbering systems. I'm going to show you base 2 and base 16, but you can do this with any base numbering system that you want. The only other one that I've really worked with is octal in the computer area, but who knows? Maybe you work with some other base, and this will work for any of those. So, what do you know about the decimal numbering system, or base 10? Well, first of all, you know that it uses the numbers, or the digits, 0 through 9. You know that each place in a number is a power of 10. Now, you might not have thought about that. You learned place value, but it's really a power of 10. You also need to know, basic math, that any number raised to the 0 power is 1. Any number raised to the first power is the number itself. So in our table here, we're looking at how to calculate place values. So in the very right, 10 raised to the 0 power is 1, right here, and 10 raised to the first power is 10. So then this is, as you can see, our exponents. This is 0, this is 1, this is 2, this is 3, and we keep on going up. Any number raised to the 0 power is 1. Any number raised to the first power is the number itself. So now we're going to get to raised to the second power. Well, in exponents, however many numbers that little number is for the exponent, that's how many of that number below that you want to multiply together. So in this case, it's 2. So 10 times 10 is 100. I know you know what that is, but bear with me. We're going to the next one, 10 to the third. Well, that's 10 times 10 times 10, and that's 1,000. So let's take now the base 10 numbering system and let's expand that. So let's put a number 1, 2, 3, 4. And you know that's 1,234. You just know that. You just don't even have to think about, if I see the number 1, 2, 3, 4, could have a comma after the 1. I know that's 1,234. But really, what are you doing? You are taking in your head, but you're just doing this so automatically because you know how to do this. You're taking what is the place value and you're multiplying that, and then you're adding them all together. Are you confused? Hang on. So if I have the number 1,234 or 1234, it is really, looking by the place values, 1 times 1,000, 2 times 100, 3 times 10, 4 times 1. So as you can see here, I've written those down. And so 1 times 1,000 is 1,000, 2 times 100 is 200, 3 times 10 is 30, 4 times 1 is 4. I add them all up together and I get 1,234. Now, when you count, you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You only have 0 through 9 to represent your number, and then at the 10 you need to carry the base to the next position. So, you know that. Let's convert that same thing to binary, and you'll see that it's exactly what you do in base 10. You just have to think, how much are you going to carry, what's the base, and what is the place value. The binary numbering system uses 0 and 1. Each place is a power of 2. So you have 2 to the 0, starting at the very right, 2 to the 0, 2 to the first, 2 squared, 2 cubed. Right? The next line, we're going to expand that. Remember that any number raised to the 0 power is 1. Any number raised to the base is the number itself. And then it's the number times the number, depending on what your exponent is. So in this case, we have 2 cubed is 2 times 2 times 2, or 8, and 2 squared is 2 times 2, or 4. So really the place values in binary are 1, 2, 4, 8. I know that sounds weird, but we're going to use the same process as we use in base 10, and you'll see that. And again, as you see it going through all the different numbering systems, we'll do base 2 and base 16. It works for anything. Works for anything. So here we go. I have, remember, in binary, I have 2. Binary is on and off. That's why the computer loves it so much. And I only have 2 numbers, 2 digits, to represent my entire numbers that I can use. Okay, really limiting. So now you know that I have to have a lot of binary digits to represent, the larger number I have, the larger number of digits I need. So let's just take an example here. I have the binary number 1011. And I'm going to figure out really what the place value of that is. And technically, I'm going to convert that to decimal in my head while I'm doing this. So again, I got 2 raised to the 0 power is 1. 2 raised to the first power is 2. When I do 2 squared, that's 2 times 2. 2 cubed is 2 times 2 times 2, which is 8. 2 times 2 is 4. All right, so here we go with figuring out what that place value is, right? Remember the number, 1011. Can you come up with what that number converts to in decimal? Let's take a look. So we have 1011. Just as we did with base 2, we're going to figure out what those place values equate to. And in essence, we're going to be converting this binary number to decimal using a table method. Okay, this is probably my favorite method. So I just place my number out there, whatever position it's in. So this is 1 times 8, 0 times 4. That's a hard one, right? 1 times 2, and 1 times 1. So then I'm going to add all those numbers up. So I have 8, 9, 10, 11. So, and this is another little thing. We're not going to say I have 1011 that's equal to 11. No, because when we're dealing with base, we really have to tell people, and how you say a binary number is just by saying the digits. So I have 1011 in base 2, converted to decimal is 11. So, and that's how we write it with those little subscripts down below. Okay, this is a little tricky. Let's count in base 2. So, 0, 1. Uh-oh, I don't have a 2. Just like in base 10, I don't have a 10. So I had to move that 1. So 1, 0 is 10 in decimal, but 1, 0 is 2 in binary. Now, you might need to stop the video, think about that a second, go back and kind of study that table and see if that makes sense. Okay, so remember, we don't have a 10 in decimal, just like we don't have a 2 in binary. So a 1, 0 is going to move into that 2's position. So 1, 0 is a 2 in binary. When I'm counting in binary, what I do is I kind of have that table in my head that I'm really counting in decimal. My head's counting in decimal, and my mouth is saying binary. Okay? I know that sounds pretty weird, but hear me out. So 0, 1, 1, 0. If I was going to convert that to decimal, that would be a 2. So 1, 0 in binary is a 2 decimal. So now I think, okay, what's a 3 decimal? And I say, okay, that's a 1 in the 2's position for binary, and the 1 in the 1's position, so 2 plus 1 is 3. So 1, 1 is 3. So how do I make a 4? Well, I have to move the 1 to the 4's position. Okay, so as I'm going through 0, 1, 1, 0, 1, 1, 1, 0, 0, that's really 0, 1, 2, 3, 4. So really I'm kind of converting that in my head so I don't get messed up. So I have 1, 0, 1, then I have 1, 1, 0, 1, 1, 1. Now I'm out. As soon as I get 1s in every single position, I got to move to that next position. Just like I have 999 in every position, I have to move, from 999, I got to move to the next position, which is 1,000. So just like I have 111, which would be a 7, I have to move to the next position, and that's the 8th position. So 1, 0, 0, 0 is 8. Now I have 1, 0, 0, 1, which is 9. So can you do, what is 10? What is the next position, what the next number in my base 10? If you said 1, 0, 1, 0, you would be correct, because that is 10. A 1, 0, 1, 0 is a 1 in the 8th position and a 1 in the 2's position, and 8 and 2 is 10. It's hard because you only have 0 and 1 to represent your number. So as soon as you try to say 2, you've got to move to the next position. Okay, place value. We're so used to decimal, you got to wrap your head around base 2. Okay, so you're really good now. You can do this. You've got base 10, known it since you started working with numbers. Base 2, maybe have a bit of understanding on that. Let's move to base 16. So instead of a lot of numbers, like in base 2 to represent something in decimal, you have really few numbers in hexadecimal to represent a very, very large decimal number. Okay, so let's think about place value. First of all, when I'm using hexadecimal, I've got 16, right? Base 16. So I'm going to use 0 through 15, just like in base 10, I use 0 through 9. I'm using really one less digit than the base. Now I don't have anything to represent 10, 11, 12, 13, 14, and 15, so I'm going to use the alphabet. And we use it, always see it in capital letters. So A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. I used to have a bookmark that had that table on it. It had A, B, C, D, E, F in a column. It had the equal sign, and then it had what each one of those was. Just because I could look at that really quick and decide. Now, as I worked with this, I certainly didn't need that crutch, but it was really good starting out. So, as we're looking at base 10, base 2, now base 16, did you notice that the numbers used in the base is always one less than the base? So I've got base 16, I'm using 15 different numbers and letters to represent that. So each place value, in base 10, it was 10. In base 2, it was 2. Guess what it is in this base 16? You're right, 16. So I've got the table of powers on my first line, I've got it expanded on the next line, and look at cubed. 16 cubed is 4,096. Wow. Okay? So, as we calculate the place values, now we're going to try to take this number, 12AB, and we are going to try to get that into some kind of decimal number, right? Here we go. So, again, here's our table, and we read the number 12AB, and probably we know that that's a hexadecimal numbering system. So, just as we did with base 10 and base 2, we figure out what place value those are each going to occupy. Again, I'm using the table method now. So, the 1 is in the 4,096th place value position. So easy to say 1s, 10s, 100s, thousands, rather than 1s, 16s, 256s, and 4,096s, but that's what you're doing. That's what you're doing. So, adding them up, you have the 4,096 because you have a 1 in that position. You have a 2 in the 256 position, so that's 512. You have a or a 10 in the 16th position, which is 160. And you have a B or an 11 in the 1's position, and so that's just 11. Adding those numbers up, you end up with that 12AB in base 10, or the 12AB in base 16 is 4,779 in base 10. Counting is fun, and I think it's easier. If you get the hang of base 2, base 16 is kind of like base 10 on steroids. So I like it a little better because now I got more numbers to play with. Before I hit 16, and when I hit 16, I got to carry 16 over the next place value and start all over again. Okay? So I go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's cool. A, B, C, D, E, F. Not a problem. Now I move over to that 16th position. So I have 1, 0. And please don't call that 10. If you're counting in hexadecimal, you do not have a 10 that is 1, 0. that is actually 16. But we're just going to say 1, 0. Now 1, 1. Now notice 1, 1 in decimal is 11, 1, 1 in binary is 3, and 1, 1 in hexadecimal is 17. So then we have 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1, A, 1, B, 1, C, 1, D, 1, E, 1, F. And then after 1F, I'm going to have to move to the next position, so that's going to be 2, 0. Now you have 0 through F to represent your numbers, and at 15, or F, once you get to that position, you can't go any higher than F for my numbers, just like I just can't go any higher than 9 for my decimal numbers. I need to carry to the next position. You're still with me? Great. Now let's convert. We've already really done that table method by that place value, and I really like that. But there is also the remainder method. I don't really care for that, but I'm going to show you how to use it. I don't think it's as fast as that table method. And I also think, if I'm under pressure, I can add quicker and more accurately than I can divide. Just saying. So I'm also going to show you a shortcut to convert between binary and decimal. I think you'll like that. So with my place values table, I've got this binary number 10101011. I've put it in the table of my place values, and I don't have in the top row, I don't have the 2 to the 0, 2 raised to the first power, 2 squared, 2 cubed, 2 raised to the 4th, 5th, 6th, 7th. I don't have that. Because I think you know how to do that by now, but I've expanded the numbers, so you really have, and the multiplication is really easy. You got ones or zeros. So I have 1 in the 128th position, I have 1 in the 32nd position, I have 1 in the 8th position, 1 each in the 2 and 1 position. So when I add those up, I get 171 base 10. So table method, again, a little practice, and I think you'll have. The remainder method is used to convert any decimal number to any base. Okay, you divide the number by the base that you want to convert. You indicate the remainder. You continue dividing by the base, so by 2 for base 2, or binary, by 16 for hexadecimal, until the quotient is 0. Now that's the one, you need to star that maybe even. You continue dividing by the base until the quotient is 0. The one reason that I don't like the division or the remainder method is that when I'm done, I think when I know it won't go in anymore, then I think I'm done, and you don't. You have to do it until the quotient is 0. You gather up the remainders for your answer, and it's the last division, that's that high order position for your result, and you have to remember that too. So not a problem. This might be something that you like to do, and I'm going to show you. So we have a base number of 163, base 10, 163. We want to go into binary. All right. So the very first thing is I take I'm looking at the bottom, and so as you do this, and if you want to do the little division symbol, the one that looks like a little house, or they call it the little house, it looks kind of fun. It looks like almost like a half a leaning tower pizza by the time you get done. So I'm going to start at the bottom, and I'm going to take 163, which is my base 10 number, and I'm going to divide it by binary base 2. Okay, so I get 81 with a remainder of 1. Then I'm going to take 81, divide it by the base, which is 2. I'm going to get 40 with a remainder 1. Now I'm going to get 40 divided by 2. That's 20 with a remainder of 0. 20 divided by 2 is 10 with a remainder of 0. 10 divided by 2 is 5 with a remainder of 0. 5 divided by 2 is a 2 remainder of 1. 2 divided by 2 is 1 with a remainder of 0. And don't forget, this is where I want to stop, because my brain says, well, I know that won't go in there, but the rules say you need to divide until the quotient is 0. So 1 divided by 2 is 0. Ding, 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 quotient is 0 now. I have a remainder of 1. And so really, if you forget that step, which I did a lot, if you forget that step, you've just dropped off the high order position when you converted. So you don't want to do that. And again, you can use the table method to check your work to make sure that that's right. So you just kind of, the table method I think works both ways. I think it works really well in figuring out the numbers, putting that 101000011 back into that table and converting that back into decimal. I think that works great for a double check. So let's go hexadecimal to decimal. So I've got the positions laid out. I want to know what ABC is. Base 16, what's at base 10? Put the ABC in there, and I have 256 times A, which is 10, 16 times B, which is 11, 1 times C, which is 12, so 256 times 10 is 2,560, 16 times 11 is 176, and 1 times 12 is 12. Add those all together, and I get 2,748. So ABC, which is a hexadecimal number, converts to 2,748 in base 10. I can also use the remainder method, and I need to divide. So now we're going to convert from binary to hexadecimal. So it takes 4 bits to represent a hexadecimal character. So we're going to use in the table, okay, back up, 4 bits to represent a hexadecimal character, right? Because if we put 1111, right, 8 plus 4 plus 2 plus 1 is what? 15, right? So that's 1 hexadecimal character. Make sense? So it takes 4 bits to represent a hexadecimal character, and I want to put in, let's say, 1011. So in my brain, I don't have to do anything with the zeros. I just have to add 8 and 2 and 1, which is 11, and 11 in base 16 is a B. So that's how I use this to figure out. It's only 4 digits, so it's kind of a little shortcut, I think, to go from binary to hexadecimal. Same thing, hexadecimal to binary. Let's say I have an ABBA. I know an A is 10, so that I need an 8 and a 2. So that's 1010. A B is an 11, so I need an 8, a 2, and a 1. So I have a 0 in the 4th position, so I have 1011. Next letter is B, next letter A, so I just repeat those. Okay, so I think it's really easy with that shortcut of 8421, 1248. I know that backwards and forwards, and that helps me convert from hex to binary and binary to hex. Wow, last slide. You made it. What is all this used for? Well, binary is used to explain IP addressing and subnetting, but you usually see it in its dotted decimal form, and you also can use binary to determine if a IP address is a class A, B, or C. Hexadecimal is used for MAC addresses, although you never really see it in any calculations. And so if you see A through F along with some numbers, probably going to be a MAC address. All these conversions are used on the CCNA exam. So there are calculators out there. In fact, there's the programmer calculator that you can get right on a Windows computer. The calculator app has, if you go into the file menu, it has a regular calculator, scientific, and programmer. Programmer lets you do this very easily. Great to check your work. But if you're going to take the CCNA exam or A+, Network Plus exams, no calculators, so you're going to have to know how to do it by hand. Hope this video was helpful, and I hope you've enjoyed numbering systems.